Hey everyone, welcome back to the channel. Thanks so much for taking the time to watch this new episode about the Archean Earth. If you enjoy this kind of long, calm, deep time content, please remember to like the video, subscribe, and share it with someone who might love science as much as you do. It really helps the channel grow and lets me keep making more episodes like this. Thank you again for being here and for all your support. By the way, I'm curious, what time of day are you listening to this, and where in the world are you watching from? In the Archean Eon, the inner part of the solar system holds a young sun that shines with power that is still growing, and the Earth moves around it in a stable orbit in a space that is quieter than before, but far from calm. The sun is the same kind of star that it will be later in time, but in this era it is slightly dimmer in total light and more restless in its outer layers. As hydrogen fuses to helium in its core, the overall energy that reaches the edges of the solar system slowly climbs. Yet during the Archean, it is still only about 3/4 of its later strength. At the same time, the magnetic activity of the young star is high, so short bursts of intense radiation and streams of charged particles are more common than in a mature phase. The Earth receives this changing output without any control over it, simply by presenting its cross-section to space as it circles the star once each year, and the amount of energy delivered to the top of the system that surrounds the planet is set mainly by distance and by the sun's evolving brightness. The radiation that leaves the surface of the sun in this time covers a wide range of wavelengths. Most of the energy comes as visible light and as infrared light, which carry warmth and illumination, but a larger share than later also travels as ultraviolet light and as soft X-rays. These higher energy forms arise from hot, magnetically active regions in the solar atmosphere where loops of ionized gas arch above the surface and reconnect. In the young sun, those regions are widespread and dynamic. So pulses of high-energy light move through space at irregular intervals. Each flare or brightening event sends a brief increase in ultraviolet and X-ray output outward in all directions, and a fraction of that power intersects the orbit of the Archean Earth. On quiet days, the flux remains lower yet steady, but the baseline in this era still includes more high-energy radiation than the modern planet receives. Over long spans of Archean time, this altered balance of wavelengths affects how the upper layers of the planetary environment absorb and filter energy, even though the total incoming power from the star is modest compared with later ages. Alongside light, there is a constant flow of particles that streams from the hot outer atmosphere of the sun. This solar wind consists mainly of electrons and protons, with a small share of heavier ions all moving outward at hundreds of kilometers per second. In the Archean, the wind is generally denser and faster, because the young star rotates more rapidly and its magnetic field lines are more tangled and open. The result is a broader and more forceful outflow that fills the space between planets with a thin, hot plasma. Near the orbit of the Earth, the pressure of this plasma shapes the boundary of the region dominated by the planet's own magnetic field, compressing it on the side that faces the sun and stretching it far out on the night side. Gusts in the wind and large eruptive events, such as coronal mass ejections, sometimes sweep past carrying clouds of magnetized plasma that buffet this boundary. When that happens, the interface between the solar wind and the planetary field shifts and vibrates, and the rate at which energy and particles cross into the near-Earth environment rises for hours or days. Over millions of years, the steady action of light and the solar wind is punctuated by rarer but dramatic visits from solid bodies. The Archean Eon follows a time of very frequent impacts when leftover planetesimals from the birth of the solar system strike the inner worlds at high rates. By the Archean, this period has eased, yet the flux of asteroids and comets near Earth remains higher than it will be in later geologic eons. The solar system still contains many small bodies on orbits that cross that of the Earth, and gravitational nudges from the giant planets and mutual interactions continue to steer some of them inward. Dust grains and sand-sized fragments sweep past the planet in great numbers, leaving only thin traces as they burn away high above the surface. Larger objects, perhaps hundreds of meters to many kilometers across, arrive much less often, but when they do, they carry large amounts of kinetic energy that must be dissipated. Their speeds, set mainly by the sun's gravity and by their own orbital paths, reach many tens of kilometers per second, so even a modest rock delivers energy comparable to that of a powerful volcanic event when it meets the planet. Cratered surfaces on the Moon and on the oldest fragments of crust that survive on Earth give partial records of this bombardment history. The number and size of the craters suggest that early in the Archean impacts are still relatively common, and that the rate declines with time as the reservoir of unstable bodies is slowly reduced. Some collisions excavate basins hundreds of kilometers wide, ejecting material out of the atmosphere and perhaps lofting vapor and molten rock into space, while countless smaller strikes roughen the outermost skin of the planet. In space around the Earth, each impact briefly adds a cloud of debris, vapor, and dust to the local environment. Before most of that material falls back, escapes, or is swept away by radiation pressure and by the solar wind. The result is a slow trend toward a cleaner orbital neighborhood, but not an empty one. Tiny grains continue to spiral inward under the action of the sun's light, and streams of cometary dust shed by icy visitors from the outer solar system cross the planet's path at intervals set by their orbits. From a broad perspective, the space environment of the Archean Earth holds fewer large disturbances than earlier times, yet remains strongly shaped by the sun and by remaining solid bodies. The sun gives off less total radiant power than it will later, but it does so with more frequent outbursts and a stronger particle wind. The region through which the Earth travels is filled with a flowing plasma, bathed in a changing spectrum of light, and threaded with the paths of dust and rock fragments left from planetary formation. All of this energy and matter reaches the outer boundary of the Earth system and sets the conditions to which the uppermost layers of the planet must respond during the Archean Eon, forming the outermost part of the chain of processes that link space to the deeper regions below. In the Archean Eon, the interaction between the young sun and the Earth continues inward from open space to the boundary where the planet's magnetic field shapes the flow of charged particles. The Earth already has a working internal dynamo driven by motion of conductive fluid in its outer core, and this dynamo generates a global magnetic field that reaches far into space. Field lines emerge near one geographic polar region, curve through space, and re-enter near the opposite region, forming a large magnetic envelope around the planet. This envelope, called the magnetosphere, stands against the solar wind that streams outward from the sun. In the Archean, the denser and faster wind presses the day side of the magnetosphere closer to the planet than in later times, while its night side tail stretches far downwind. The overall shape is set by a balance between the pressure of the solar wind and the strength of the terrestrial magnetic field. Rock samples from later Archean and slightly younger times preserve traces of magnetization that indicate that a substantial field already exists, although its exact strength and structure at every moment remain uncertain. Some studies suggest that the field may be comparable to or somewhat weaker than in more recent Earth history, while still strong enough to stand off most of the impinging plasma. This field controls how energy and particles from the Sun enter the near-Earth environment. Where the magnetic field of the solar wind and that of the Earth point in directions that favor interaction, a process called magnetic reconnection links some of the interplanetary field lines to those anchored in the planet. Once connected plasma from the solar wind can move along these paths into the magnetosphere and deposit energy. The boundary where this often happens, known as the magnetopause, lies only a few Earth radii from the planet on the day side during the Archean because the external pressure is high. Each strong gust in the solar wind and each passing eruptive cloud from the Sun can push this boundary further inward, shrink the day-side cavity, and load more energy into the entire system. Within the magnetosphere, charged particles follow the curved magnetic field lines, spiraling around them as they drift. Some become trapped and form radiation belts, regions where particles bounce between mirror points in the northern and southern magnetic regions. In an Archean setting with strong solar wind input, these belts may be more variable and more heavily populated, though direct evidence from this time is absent and conditions must be inferred from physical models and by analogy with later and present behavior. When energy accumulates in the magnetotail on the night-side reconnection, there can also occur releasing stored magnetic energy and driving plasma inward along field lines toward the polar regions. Precipitating electrons and ions then enter the upper atmosphere near the magnetic poles. Their collisions with atoms and molecules in the thin, high air deposit energy heat, those layers, and change their ionization state. Although the visible manifestations of such processes in the Archean sky cannot be observed today, the underlying physics of particle precipitation and energy transfer is expected to be similar to that in later times, with some differences set by the different composition and density of the early atmosphere. Above the neutral atmosphere lies the ionosphere, a region where solar radiation strips electrons from atoms and molecules and creates a partially ionized gas. In the Archean, enhanced ultraviolet and X-ray flux from the young sun raises ionization rates, especially on the day side. This denser ionospheric plasma interacts with the magnetosphere through electrical currents that close along the field lines and through the conducting upper atmosphere. As currents flow, they generate secondary magnetic fields that slightly modify the overall configuration and can feed back on how the magnetosphere responds to changes in the solar wind. The ionosphere also acts as a boundary where waves and instabilities excited in the magnetosphere can dissipate. Energetic particles and fields drive random fluctuations, and some of that energy is converted to heat, raising the temperature of the upper atmosphere and influencing how gas escapes to space. Electric fields that extend from the magnetosphere into the ionosphere can accelerate ions upward along open field lines, particularly near the polar caps, allowing light species, such as hydrogen, to escape more easily. Over long spans of Archean time, the cumulative loss of light gases through these polar outflow channels contributes to the gradual change of atmospheric composition, while heavier gases remain more strongly bound by gravity. The magnetosphere also shapes how much of the early atmosphere is shielded from direct impact by the solar wind. Without a magnetic field, the wind can erode an atmosphere through direct mechanical stripping, as it does to some degree on unmagnetized bodies. In the Archean Earth, the presence of a global field redirects most of the incoming plasma around the planet, reducing this kind of loss. However, the shielding is not complete. At high magnetic latitudes where field lines are open and connect directly to interplanetary space, the solar wind can interact more strongly with the upper atmosphere. Here, transfer of momentum and energy from the plasma flow can still drive escape and modify the structure of the upper layers. The balance between protection and exposure depends on the exact strength and configuration of the field and on the intensity of the solar wind quantities that vary over time and are only partly constrained for the Archean. The continual movement of conductive plasma in the magnetosphere and ionosphere also induces electrical currents in the planet's crust and oceans. In the Archean, with large ocean basins already present and crust of various ages and compositions, such induction effects may already play a role in distributing energy and subtly heating conductive layers. Although this contribution is small compared with internal heat from the planet's formation and from radioactive decay. Still, on shorter timescales, strong geomagnetic disturbances driven by solar activity can alter the state of the upper atmosphere, its temperature profile, and its capacity to reflect or absorb certain frequencies of electromagnetic waves. Even though there are no technological systems in this time to sense such changes, the physical couplings between magnetosphere, ionosphere, and atmosphere operate as part of the linked system that governs how energy from space moves inward. Overall, during the Archean Eon, the region where the Earth's magnetic field meets the solar wind acts as a dynamic filter and mediator between space and the atmosphere below. The young sun delivers a stronger and more variable stream of particles and high-energy radiation than in later ages, and the terrestrial dynamo provides a substantial but evolving magnetic shield. Together, they produce a pattern of space weather that is more intense and more frequent than that experienced in modern times, with repeated episodes of enhanced energy input at high altitudes. This outer interaction zone does not determine the detailed state of the lower atmosphere by itself, but it sets boundary conditions for the uppermost layers of gas shapes, the long-term escape of light species, and feeds energy and charged particles downward, forming the next link in the sequence that connects conditions in interplanetary space to the air, water, and rock of the Archean Earth. From the outer boundary shaped by the magnetosphere, the environment of the Archean Earth continues inward into a region where space gradually gives way to very thin air. Far above the surface, in the highest part of the atmosphere, gas becomes so rarefied that a single molecule can travel a long distance before colliding with another. This region, called the exosphere, marks the transition where particles with enough speed can break free from the pull of gravity and escape into space. In the Archean, the composition of the gas that reaches this height is strongly influenced by the young sun's intense ultraviolet and X-ray radiation. High-energy photons break apart molecules such as water vapor and methane in the upper atmosphere, freeing light atoms, especially hydrogen. These hydrogen atoms, warmed by the same radiation and by collisions, often acquire speeds that exceed the escape speed, so they drift upward and do not return. Over long spans of time, this continuous leakage of hydrogen helps to dry the planet and shift its overall chemical balance, because hydrogen is one part of many reduced compounds. As hydrogen is lost, the remaining material tends to become more oxidized, even if free oxygen gas remains scarce in the lower atmosphere. Just below the exosphere lies the thermosphere, a region where the few remaining atoms and molecules absorb high-energy radiation and can reach very high kinetic temperatures. In the Archean, the flux of extreme ultraviolet light from the sun is stronger than in later times, so this heating is more intense. The gas here is extremely thin, so the total amount of heat content is small, even though the energy per particle is high. Collisions are infrequent, and particles follow long curved paths under the combined influence of gravity pressure gradients and electric and magnetic fields. The composition in this height range is lighter than at lower levels, because gravity allows lighter species, such as hydrogen and helium, to reach higher altitudes more easily than heavier nitrogen and carbon dioxide molecules. At the same time, ionization by solar radiation is common in this rarefied gas. So many particles carry electric charge, blurring the boundary between neutral upper atmosphere and ionosphere. Escape processes operate here in more than one way. In addition to simple thermal escape of fast-moving hydrogen described by kinetic theory, there are non-thermal paths driven by the interaction with the magnetosphere and solar wind. When energetic particles from space enter along open magnetic field lines, they can transfer energy to atmospheric constituents through collisions. Some reactions cause chemical changes, while others knock atoms and ions to speeds that allow them to leave the planet. Charge exchange events, where a fast ion from the solar wind swaps an electron with a neutral atmospheric atom, can convert that neutral into a fast ion that is then carried away by magnetic fields. In the polar regions where field lines open into space upward, electric fields can accelerate ions and create a slow but persistent outflow, sometimes called a polar wind. In the Archean, this combination of elevated solar radiation, stronger solar wind, and a working but evolving magnetosphere likely gives rise to higher escape rates of light species than in more recent times, although the exact values remain uncertain and depend on details that cannot be directly measured for this distant era. Deeper in the atmosphere, the density increases and collisions between molecules become more frequent. Here, the gas behaves more as a continuous fluid, and local temperature and composition can be defined over modest distances. The Archean atmosphere is thought to be dominated by nitrogen gas with significant amounts of carbon dioxide water vapor and varying amounts of methane and other volcanic gases. This picture arises from several lines of geological evidence, including ancient soils, mineral assemblages, and isotopic ratios in sedimentary rocks, which reflect the pressure and composition of the air that interacted with surfaces and waters. However, these records are incomplete and often altered by later processes, so the precise concentrations of each gas remain uncertain. Most studies suggest that free oxygen gas is extremely low, far below modern levels, and that methane may reach levels high enough to influence climate and photochemistry strongly. In the upper reaches of this denser envelope above the main region of clouds and weather, but below the very thin thermosphere, ultraviolet light from the sun continues to drive chemical reactions. Photons with enough energy break chemical bonds in gases such as methane, water vapor, and carbon dioxide, producing reactive fragments called radicals. These radicals recombine in various ways, building a spectrum of more complex molecules. Some products are short-lived and feed into further reactions, while others can condense or coagulate into tiny solid or liquid particles. Under some combinations of methane, nitrogen, and other gases, these processes can generate an organic haze, a population of fine particles that form high in the atmosphere. In the Archean, with relatively strong ultraviolet flux and potentially high methane levels, such hazes may form episodically or persistently, though the exact timing and thickness remain topics of active study. If a haze layer is present, it can have several effects. It can absorb and scatter incoming solar radiation, altering how much light reaches deeper layers and changing the spectral distribution of that light. It can also provide surfaces on which further chemical reactions occur, including reactions that remove some gases from the atmosphere by condensing them onto particles that eventually fall out. The presence or absence of such hazes in different Archean intervals depends on the balance between methane production, destruction by ultraviolet light, vertical mixing, and removal processes. Because direct observations of these hazes are not possible. In the modern world, scientists rely on atmospheric models, laboratory experiments that simulate Archean gas mixtures under strong ultraviolet radiation and indirect clues from sedimentary rocks to estimate their behavior. At these altitudes, radiative heating and cooling processes establish a vertical temperature structure that differs from that of a modern ozone-rich atmosphere. In later times, an ozone layer absorbs ultraviolet light in the middle atmosphere and creates a distinct region where temperature increases with height. In the Archean, with very little oxygen and ozone, that pattern changes. Instead, heating from ultraviolet absorption by other gases and by any organic haze, along with cooling by infrared emission from carbon dioxide and water vapor, sets the profile. The absence of a strong ozone layer means that more short-wavelength ultraviolet radiation can penetrate to lower heights, though it is still attenuated by other absorbers. This altered balance of absorption and emission defines the boundaries between atmospheric layers and influences the heights where specific chemical species are most abundant. The upper atmosphere also communicates with lower levels through waves and turbulence. Disturbances generated in the denser air below, such as gravity waves driven by topography or convection, can propagate upward and deposit energy and momentum at great heights. In the Archean, the patterns of such waves will reflect the distribution of early oceans and land fragments which are still limited but present. When the waves break in the upper atmosphere, they contribute to mixing and to the redistribution of heat, helping to maintain the overall structure of winds and temperatures in these thin layers. At the same time, variations in solar radiation, solar wind input, and magnetospheric conditions modulate the ionization and temperature at the top, sending changes downward. In this way, the Archean upper atmosphere functions as an interface region where energy from space is absorbed transformed and partly lost, while the bulk air of the planet begins to assert its role as a reservoir of mass and chemical species. Over geological time, the continuous escape of hydrogen and possibly other light gases through the exosphere, combined with photochemical reactions in the upper layers, slowly modifies the atmosphere's composition. The rate of change is modest on human timescales, but important over hundreds of millions of years. This gradual leakage and processing set broad constraints on how much water and reduced gases the Archean Earth can retain, and how the redox state of the surface environment evolves. Below these heights, denser layers of air take shape, holding clouds, weather systems, and the main greenhouse gases that control near-surface temperature. But in the Archean Eon, the behavior of those deeper layers remains tied to the conditions imposed from above by the structured, actively heated, and slowly escaping upper atmosphere. In the Archean Eon, the bulk of the atmosphere lies below the thin, escaping upper layers and holds the air that controls most of the light and heat that reach the surface. At these heights, the gas behaves as a continuous fluid, and its pressure, temperature, and composition vary smoothly with altitude and location. The total pressure at the surface is not known with certainty, because rock records from this time do not preserve a direct gauge, but several lines of evidence suggest that it is at least comparable to modern values and may be higher, with nitrogen gas making up most of the mass. Nitrogen is relatively inert under many surface conditions, so it acts mainly as a background gas that sets pressure and influences the broad behavior of sound winds and the boiling point of water, rather than as a very active chemical player. Mixed with this nitrogen are gases that participate more directly in climate and surface chemistry. Carbon dioxide is one of the major such species. Volcanic outgassing from the hot interior releases it steadily, and there are as yet no large forests or complex ecosystems to draw it down and bury it in the form of organic carbon or vast carbonate deposits on continents. Geochemical evidence from ancient marine sediments and from minerals that form in soils and weathered rocks suggests that carbon dioxide concentrations are much higher than in later eras, though the exact level is not firmly known. Some studies are consistent with partial pressures that are many times greater than modern values, while others point to more moderate amounts. But in all reasonable scenarios, carbon dioxide plays a key role in trapping outgoing infrared radiation and helping to keep the surface warm enough for liquid water under a dimmer sun. Water vapor is another important component of the Archean air. Its abundance at any given place and time depends strongly on temperature and the presence of surface water, which is already widespread in oceans and smaller basins. But it also depends on circulation patterns that will be examined more closely in later sections. Near the surface above warm seas, evaporation loads the air with moisture, while rising motion and cooling cause some of that water vapor to condense higher up, releasing latent heat and forming clouds. In a global sense, water vapor acts as a potent greenhouse gas, trapping infrared radiation and amplifying the warming provided by carbon dioxide. The balance between its supply through evaporation and its removal through condensation and precipitation creates a dynamic cycle that ties the atmosphere to the oceans and to any exposed land. Alongside these common gases, the Archean atmosphere likely contains significant amounts of methane. Methane can be produced abiotically in high-temperature reactions in the mantle and crust and released by volcanic and hydrothermal systems. In addition, by the Middle and Late Archean, there is evidence for microbial life that uses pathways which generate methane as an end product, although the exact timing and strength of these biological sources remains under study. Even in the earlier Archean, before clear fossil traces of such metabolisms appear, reduced gases from the interior can contribute to methane in the air. Methane is highly effective at absorbing infrared radiation, and because it has strong bands in parts of the spectrum where carbon dioxide and water vapor are less active, it can supplement their effect and raise the surface temperature. The relative amounts of methane and carbon dioxide in the atmosphere are important not only for climate, but also for the way the atmosphere interacts with sunlight at shorter wavelengths. When ultraviolet light from the young sun strikes methane molecules in the upper and middle atmosphere, it breaks some of them apart into radicals, which then undergo a series of reactions that build progressively more complex hydrocarbons. These molecules can polymerize and ultimately form small solid particles or heavy liquid droplets composed of organic material. Once formed, these particles can grow by colliding with each other and by condensing further products onto their surfaces, and they can be carried by vertical motions to altitudes where they are stable for a time. Under conditions where the ratio of methane to carbon dioxide exceeds a certain threshold, models and laboratory experiments suggest that a thick layer of such organic particles can form, creating a global haze. In the Archean, such a haze may appear and disappear over geological time as volcanic activity, seafloor processes, and early biological sources change the flux of gases to the atmosphere. When present, the haze influences the way the atmosphere processes solar radiation. The tiny particles scatter visible light in many directions and absorb ultraviolet light strongly. As sunlight enters the atmosphere, part of it interacts with the haze before reaching the lower layers, so the spectrum and intensity of light that arrive near the surface change. The haze can reduce the direct sunlight at the surface, leading to a softer, more diffuse illumination and lowering the amount of ultraviolet radiation that penetrates to low altitudes. At the same time, by absorbing ultraviolet and some visible light high in the atmosphere, the haze warms the layers where it resides. This heating can alter the vertical temperature profile and the stability of the atmosphere, potentially influencing the heights at which convection develops and the formation of cloud layers. It also leads to infrared emission from the haze layer itself, sending energy both outward to space and downward toward the lower atmosphere. The net climate effect of the haze emerges from a balance between the shielding and cooling associated with reduced sunlight at the surface and the warming from absorption and infrared re-emission. In some regimes, the haze can act in an overall cooling sense, reducing temperatures at the ground even in the presence of strong greenhouse gases. In others, with different optical properties and gas concentrations, the combined system of greenhouse gases plus haze can maintain surface temperatures that permit liquid water despite the faint sun. Because direct physical samples of Archean air do not survive these outcomes, are assessed using coupled climate and photochemistry models constrained by what is known from rocks and isotopes. In addition to methane-derived organics, the Archean atmosphere contains other reduced gases from volcanic sources such as hydrogen carbon monoxide and various sulfur-bearing species. Hydrogen contributes to the greenhouse effect through collision-induced absorption, especially when mixed with nitrogen, but it is also prone to loss at the top of the atmosphere, as discussed earlier. Carbon monoxide participates in redox chemistry and can act as a substrate for some early metabolisms. Sulfur gases, including hydrogen sulfide and sulfur dioxide, can be oxidized in the atmosphere to form sulfate aerosols, which also scatter sunlight and influence cloud microphysics. The relative importance of these different aerosol types depends on the balance of volcanic activity, methane levels, and background oxidizing capacity of the air. The Archean oxidizing capacity is low because free oxygen gas is scarce. So many reactive molecules persist longer in the atmosphere than they would in a more oxidizing setting. This leads to longer chemical lifetimes for methane and other reduced gases, helping them reach higher concentrations. But it also means that some pathways that dominate modern atmospheric chemistry are absent or greatly reduced. Ozone, which in later times forms a distinct layer that absorbs ultraviolet light and defines a separate atmospheric region, is almost entirely missing, leaving other molecules and haze particles to perform that role. The lack of ozone also alters the temperature structure at middle altitudes, since there is no strong local source of heating from ultraviolet absorption by that species. Instead, heating and cooling there reflect a combination of carbon dioxide, water vapor, methane, and aerosol interactions with radiation. The overall vertical structure of the Archean atmosphere can still be divided into layers based on how temperature changes with height, but the detailed profiles and the heights of transitions differ from the modern case. Within this dense envelope of nitrogen, carbon dioxide, water vapor, methane, and trace gases, the stage is set for more familiar weather processes, including the formation of clouds, the movement of storms, and the exchange of heat and moisture between surface and sky. The particular mix of greenhouse gases and organic haze present at any time sets the background conditions under which those weather systems operate, defining the amount and quality of light that reaches the surface and the baseline temperature against which local variations occur. In the Archean Eon, this composition and the associated photochemistry form a central part of how the planet functions as a system linking volcanic and biological gas sources, solar radiation, and long-term climate in a way that is constrained by physical laws but remains partly hidden, reconstructed from the incomplete record preserved in ancient rocks and minerals. In the Archean Eon, the main weather-bearing part of the atmosphere lies where air is dense enough for clouds to form and for winds to move large masses of gas and water. This region reaches from the surface up to heights of several to perhaps more than 10 kilometers, where rising air parcels cool enough to lose buoyancy, and where most clouds are confined. Within this layer, temperature generally decreases with altitude at a rate set by the balance between radiative heating cooling and the release of latent heat when water vapor condenses. The exact vertical gradient in the Archean is not directly recorded, but physical laws that govern convection and the known presence of liquid water at the surface indicate that rising moist air still cools as it ascends, reaches levels of saturation, and forms clouds. The gases present here, mainly nitrogen, carbon dioxide, water vapor, and methane, set the background conditions for this process. High concentrations of greenhouse gases help maintain surface temperatures that allow evaporation from widespread oceans, while the overlying air is cool enough at some height to support condensation. As a result, a continuous cycle of evaporation, condensation, and precipitation operates, linking the atmosphere tightly to the surface reservoirs of water. Clouds in the Archean form when supersaturated air meets small particles that serve as condensation nuclei. These particles include sea salt crystals lifted from the ocean's surface by breaking waves, volcanic ash, and sulfate droplets injected by eruptions, and possibly fragments of organic haze that have settled from higher levels. Water vapor condenses first into tiny droplets that are too small to fall rapidly. As they collide and coalesce, some grow to sizes where gravity overcomes the upward motion of air, and they begin to fall as rain. In colder regions of deep clouds, freezing may occur, forming ice particles that can also grow and fall. Though the detailed balance between liquid and ice in Archean clouds depends on the local temperature profile and remains a subject of modeling rather than direct observation. The absence of land plants and the presence of different aerosol sources than in the modern world change the typical size and composition of cloud condensation nuclei, which can affect cloud optical properties and lifetime. However, the basic mechanisms of droplet formation, growth, and fallout follow the same thermodynamic and microphysical rules that operate in any nitrogen-dominated atmosphere with abundant water vapor. Over the Archean oceans, which cover most of the surface, strong heating in low-latitude regions drives persistent upward motion. Warm, moist air rises in broad columns, cools, and condenses to form thick cloud systems. These convective clouds release latent heat as water vapor turns to liquid, further fueling the updrafts. The released heat helps to maintain tall cloud towers and extensive anvil-shaped upper layers, although the exact shapes cannot be known from this distance in time. When downdrafts form as cooled air and falling rain drag momentum downward, they bring drier air from aloft toward the surface and complete local convective circulations. Such deep convection likely organizes into bands and clusters that drift with the prevailing winds, producing regular patterns of storms in some regions and relatively clear skies in others. Lightning produced when charge separation develops inside strong convective clouds almost certainly occurs because the required processes depend primarily on collisions between ice particles and graupel in turbulent cloud interiors, which are expected whenever vigorous convection reaches levels cold enough for freezing. Lightning in the Archean injects nitrogen oxides into the atmosphere and provides local bursts of high-temperature chemistry. But these contributions are modest compared with the larger-scale budgets of major gases. At the surface, rainfall from these clouds supplies fresh water to the upper ocean and to any exposed land fragments. Geological evidence from Archean sedimentary rocks, including features interpreted as ancient river channels, deltas, and ripple-marked shorelines, indicates that liquid water flows across the surface and that repeated wetting and drying cycles occur. These landforms show that precipitation must be sufficient and frequent enough in at least some regions to feed streams and sustain erosion. On small proto-continents and volcanic islands, storms deliver heavy rains that run off along slopes, carve channels, and transport sediment downslope into coastal basins. In low-lying coastal zones, alternating periods of rain and clear weather allow standing pools to fill and evaporate, leaving mineral deposits that record the chemistry of both water and air. The broader circulation of the Archean atmosphere is controlled by the balance between solar heating, infrared cooling, planetary rotation, and the distribution of oceans and land. Because the sun is fainter, the equator to pole temperature contrast may differ from that of later times, but strong greenhouse warming and the efficient mixing of heat by oceans and winds likely maintain a climate where liquid water is stable over large areas. In response to differential heating, large-scale circulation cells form similar in broad pattern to modern Hadley and mid-latitude cells, though their exact widths and strengths are set by the specific rotation rate and thermal structure of the Archean Earth. In equatorial regions, rising motion dominates with air diverging aloft toward higher latitudes. At some distance from the equator, cooling causes air to descend, creating belts of relatively dry, high-pressure conditions. Further poleward, additional overturning cells and jet-like bands of strong winds can arise where temperature gradients and planetary rotation combine to support them. These features steer storm tracks and influence where clouds and rainfall tend to form over long periods. Over the largely oceanic surface, evaporation from warm waters supplies moisture to the lower atmosphere. When winds blow persistently in one direction, as along the flanks of circulation cells, they can create zones of enhanced evaporation and cloud formation on the windward sides of any land areas they encounter, and rain shadows on the leeward sides. Even though Archean continents are small and perhaps scattered, they still perturb the flow and create local variations in cloudiness and precipitation. Their darker or lighter surfaces, depending on rock type and any coverings, also modify how much solar radiation is absorbed or reflected, which feeds back slightly on local temperature and boundary layer stability. Volcanic activity is more intense on average than in later eras, and this has a direct impact on weather in the short term and on the statistics of clouds and storms over longer intervals. Large eruptions can inject ash particles and sulfur-bearing gases high into the atmosphere. The ash settles relatively quickly, but sulfate aerosols formed from volcanic gases can persist in the upper troposphere and lower stratosphere for months to years. These aerosols scatter incoming sunlight, sometimes leading to temporary surface cooling, and provide additional nuclei for cloud droplet formation. After major eruptions, some regions may experience brighter, more reflective clouds and slight shifts in rainfall patterns. Over geological time, the repeated influence of many such events contributes to the overall aerosol background and to the variability of cloud properties in the Archean atmosphere. The day-to-night cycle imposes another pattern on Archean weather. During the day, solar heating of the surface drives turbulent mixing in the lowest part of the atmosphere known as the boundary layer. Over land, this mixing can be especially vigorous when rock surfaces heat strongly under the sun, while over ocean, the response is moderated by the high heat capacity of water. At night, radiative cooling causes the surface and the air just above it to cool, leading to more stable stratification and a reduction in turbulence. These daily variations influence the growth and decay of shallow clouds, the formation of fog over cool surfaces, and the timing of convection. Seasonal cycles controlled by the tilt of the Earth's axis and the distribution of continents and oceans further modulate patterns of temperature and rainfall, although the exact details of Archean seasonality remain uncertain due to the limited record. Taken together, these processes create an atmosphere in the Archean that is far from static. Air continuously moves heat and moisture from place to place, clouds form, and dissipate, storms arise and decay, and precipitation returns water to the surface. While many details of specific storm tracks, cloud morphologies, and regional climates are beyond the reach of current evidence, the broad picture that emerges from physical reasoning and from the sedimentary record is one of an active weather system. This system operates under boundary conditions set by a different sun, different greenhouse gas levels, and a different distribution of land and sea than in later times, but it still follows the same fundamental fluid and thermodynamic principles, providing the immediate atmospheric environment that overlies the Archean oceans and fragments of crust. In the Archean Eon, the climate of the Earth is set by a balance between incoming solar radiation, outgoing infrared radiation, and the way the surface and atmosphere exchange heat and moisture. At the top of the atmosphere, the young sun delivers less total energy than in later times, roughly 3/4 of the modern value, simply because fusion in the stellar core has not yet raised its luminosity to the level seen today. This reduced input alone would tend to keep the planet colder, perhaps cold enough that surface water would freeze globally if the atmosphere were the same as in later eras. However, the Archean atmosphere is not the same. It contains higher concentrations of greenhouse gases, especially carbon dioxide and methane, and a significant amount of water vapor over warm oceans. These gases absorb some of the infrared radiation that the surface and lower atmosphere emit, then re-emit it in all directions, including back downward. In this way, they reduce the efficiency with which the planet loses heat to space and raise the equilibrium temperature at the surface. The exact mix of these gases, and thus the precise surface temperature, varies over the long duration of the eon and is constrained mainly by indirect geological indicators such as the types of minerals that form in weathering profiles, the presence of liquid water, derived sediments, and the isotopic composition of certain rocks. These indicators point to surface conditions that support liquid water over vast regions and to temperatures that are often warmer than modern global averages, even in the presence of the fainter sun. At the same time, reflective elements in the Earth system, such as cloud surface ice and the albedo of rock and water, determine how much of the incoming solar radiation is absorbed versus reflected back to space. Dark ocean water absorbs most of the sunlight that reaches it, while lighter rock and any ice or snow surfaces reflect more. In the Archean, the distribution of these surface types differs from later times. Because continents are smaller and more scattered, and large ice sheets, when present, are limited in time and extent. This arrangement likely leads to a relatively low average planetary albedo, especially during intervals when organic haze in the atmosphere is thin or absent. Clouds complicate this picture because they both reflect sunlight cooling the surface and trap infrared radiation warming it. The net effect of clouds depends on their height, thickness, droplet size, and spatial coverage. Low, thick clouds tend to cool more than they warm, while high, thin clouds can have a net warming influence. In the Archean, the composition and size distribution of cloud condensation nuclei differ from later eras due to the lack of land vegetation and the dominance of volcanic and marine aerosol sources. So cloud properties are not identical to modern ones. Still, there is a dynamic balance in which clouds form preferentially over regions of strong evaporation and convection, then dissipate as air dries and subsides continuously, adjusting the reflection and trapping of radiation in response to underlying circulation and surface conditions. Organic haze, when present in the upper atmosphere, adds another layer of complexity. It can raise the effective planetary albedo by scattering sunlight, particularly at shorter wavelengths, while also absorbing certain bands of light and re-emitting energy in the infrared. In some regimes, a thick haze may reduce the amount of solar radiation that reaches the surface, enough to offset part of the greenhouse warming from carbon dioxide and methane. In others, a thinner haze or different particle properties may permit a warmer surface. The formation of haze depends on the ratio of methane to carbon dioxide and on the intensity of ultraviolet radiation, both of which can change with volcanic gas fluxes, seafloor processes, and the activity of early microbial life that produces or consumes gases. Over millions of years, shifts in these factors can move the climate system between states with clearer skies and states with more substantial upper atmospheric haze, each with different surface energy balances. The oceans play a major role in regulating climate by storing and transporting heat, though the detailed circulation patterns belong to another part of the system and are not treated here. In terms of energy balance, the high heat capacity of seawater allows it to absorb large amounts of heat during times and seasons of net gain and to release that heat later during periods of net loss. This buffering smooths out temperature variations on daily and seasonal timescales and helps maintain relatively stable conditions in the lower atmosphere. When sunlight warms the surface layer of the ocean, that warmth is gradually mixed downward by wind-driven turbulence and by convective overturning when surface water cools and becomes denser. At the same time, evaporation cools the surface by removing heat, and the latent heat carried away in water. Vapor is later released when condensation occurs in clouds. This movement of latent heat from surface to atmosphere and then from lower to higher levels is a key component of the vertical energy transport in the Archean climate system. Volcanic activity and long-term tectonic processes influence the surface energy balance by setting the flux of greenhouse gases to the atmosphere and by altering the arrangement of continents and ocean basins. Active volcanic regions release carbon dioxide, methane, hydrogen, sulfur gases, and water vapor. Over long periods, the accumulation of these gases can raise the greenhouse effect, while chemical weathering of silicate rocks on land and in shallow seafloor settings can remove carbon dioxide by turning it into carbonate minerals. The rate of this weathering depends on temperature, rainfall, and the availability of fresh rock surfaces. In the Archean, with smaller but likely more active continents and strong volcanic input, the balance between carbon dioxide supply and removal may shift repeatedly, leading to intervals when greenhouse warming is strong and others when it is somewhat weaker. Evidence from some Archean rock formations suggests that the planet experiences at least one significant glaciation near the end of the eon, implying that under certain combinations of lower greenhouse gas levels, possible changes in haze, and perhaps altered continental configurations, the climate can cool enough for ice to form at high latitudes or elevations. These episodes show that the Archean climate system is capable of multiple states, and that the same basic energy balance equations can yield different outcomes under different boundary conditions. On shorter time scales, the distribution of heat between equator and poles and between day and night is managed by atmospheric circulation. The equatorial region receives more solar radiation on average than higher latitudes, and this differential heating drives large-scale overturning cells that move warm air poleward aloft and return cooler air equatorward near the surface. This movement helps to redistribute energy and reduce temperature contrasts. Stronger greenhouse warming can reduce the equator to pole gradient by retaining more heat at higher latitudes, while periods with altered atmospheric composition or surface reflectivity can sharpen or soften this gradient. At the same time, the rotation of the Earth causes moving air masses to experience deflection, shaping zonal wind patterns and limiting the extent of single overturning cells so that multiple bands of prevailing winds arise. These winds then interact with surface features to influence where warm and cool regions develop. Over the vast Archean oceans, sea surface temperatures respond to the combined influences of solar input, atmospheric back radiation, evaporation, and mixing. Warmer regions under intense sunlight host higher evaporation rates and more frequent deep convection, which in turn form more high clouds that alter outgoing long-wave radiation and reflect some sunlight. Cooler regions receive less evaporation and may develop different cloud types. This arrangement forms a feedback loop. Changes in sea surface temperature affect cloudiness and moisture distribution, which in turn modify the local radiation budget and can either amplify or damp the original temperature differences. Similar feedbacks operate over land, where the albedo and heat capacity of exposed rocks and any coatings that develop on them influence the local absorption of sunlight and the rate at which heat is returned to the atmosphere. Over geological time, internal heat flow from the planet's interior also affects the surface energy budget, though in a more indirect way than solar radiation and greenhouse gases. In the Archean, the internal heat flow is higher because radioactive isotopes that provide a significant part of the internal heat have not yet decayed to present levels. This elevated internal heat supports more widespread volcanism and faster tectonic processes, which in turn shape the atmosphere through gas release and the creation of new crust. Direct geothermal heat flux at the surface is small compared with solar input when averaged globally, but it can be locally significant in regions of intense volcanism and hydrothermal circulation. Even there, however, it is the gas composition changes that mainly influence climate, not the direct addition of thermal energy at the surface. Overall, the Archean surface energy balance emerges from the interplay between a fainter but more active sun, a greenhouse gas-rich atmosphere possible, organic and sulfur-based hazes, clouds of varying type and coverage, and the thermal buffering of extensive oceans. Under most plausible combinations of these factors, the system settles into a state with liquid water oceans and a climate that is often warmer than that of later times, yet still capable of shifts toward cooler phases when greenhouse gas levels fall or reflective components increase. Although many quantitative details remain uncertain, the fundamental processes that control the gain and loss of energy at the top of the atmosphere within the air column and at the surface operate in the same way as in other eras, providing a physically consistent framework for understanding how the Archean Earth maintains temperatures that support liquid water and active weather, in spite of the reduced luminosity of the young sun. In the Archean Eon, the surface of the Earth is dominated by oceans that wrap around most of the planet, forming a continuous shell of liquid water that interacts with the atmosphere above and the solid crust below. The exact global distribution of these oceans is not known in detail because only fragments of Archean crust survive and they have been altered by later processes. But geological evidence shows that open seas, shallow continental margins, and some emergent land are already present. The oceans are warm in many intervals, significantly warmer than most modern surface waters, because high concentrations of greenhouse gases and strong geothermal heat flow help compensate for the reduced luminosity of the young sun. Surface temperatures likely vary with latitude and with proximity to volcanic and hydrothermal regions, but large areas of the ocean remain above the freezing point of water, allowing waves, currents, and weather-driven exchanges with the atmosphere to operate continuously. The uppermost part of the ocean, often called the mixed layer, is where wind waves and convection stir the water and keep temperature and salinity relatively uniform down to tens or in some places, perhaps hundreds of meters. Winds that blow over the ocean's surface transfer momentum to the water, generating waves and setting the upper water in motion. Small ripples grow into larger waves as energy is added, and breaking waves increase the exchange of gases and heat between air and sea by renewing the thin surface layer, injecting bubbles and lofting tiny droplets into the atmosphere. These mechanical processes are controlled by wind speed fetch and the density difference between air and water variables that exist in some form in every era. In the Archean, the pattern of winds is set by the same pressure gradients and planetary rotation that shape atmospheric circulation, so bands of stronger and weaker surface winds drive corresponding variations in wave climate and in the strength of surface currents. Where winds blow persistently in one direction, surface water is pushed along, forming broad current systems that can span large portions of ocean basins. Because the Earth rotates, moving water experiences a deflecting force that turns currents to one side, creating large-scale gyre-like circulations in the upper ocean. The exact arrangement of Archean continents and ocean basins is not fully known, so the precise paths of these currents cannot be reconstructed, but physical principles and numerical models show that any planet with rotation winds and large water-covered areas will develop similar organized flow structures. These currents redistribute heat, transporting warm surface water away from regions of net energy gain toward cooler regions where heat is lost to the atmosphere and to space. They also carry dissolved substances, including salts, nutrients, and gases, tying regional ocean chemistry into a global system. Beneath the mixed layer, where direct wind stirring is weaker, temperature and density gradients become stronger and tend to inhibit vertical mixing. However, in the Archean, higher geothermal heat, flow, more active sea floor spreading, and extensive hydrothermal circulation can reduce the stability of deep ocean stratification, especially near mid-ocean ridges and volcanic plateaus, by injecting heat and chemically altered water into the deep sea. While the fine-scale structure of stratification belongs to deeper layers, the surface ocean still connects to these processes through large-scale overturning and mixing events that slowly exchange water between shallow and deep reservoirs. Superimposed on the wind-driven currents is the action of tides, which play a special role in the Archean, because the moon orbits closer to the Earth than in later times. Geological and dynamical models indicate that tidal forces decrease as the Earth-Moon distance grows, and during the Archean, this distance is significantly smaller, so the gravitational pull of the moon on the oceans is stronger. As the Earth rotates under this gravitational field, two tidal bulges of water form roughly along the line joining Earth and Moon, one facing the Moon and one on the opposite side, and these bulges move relative to the seafloor and emergent land. The Sun also contributes to tides, but in this era, the lunar component dominates due to the shorter Earth-Moon distance. Stronger tides mean that the range between high tide and low tide is greater in many locations, and tidal currents in narrow straits around islands and along continental margins are more energetic. These currents stir the water column, enhance mixing between surface and deeper layers, and increase the delivery of nutrients and chemical species from the seafloor to the upper ocean. In shallow coastal seas, repeated tidal flooding and draining reshape sediments build sand and mud bars and create complex intertidal environments where water depth and exposure change on daily time scales. Rock structures in some Archean sedimentary sequences, including rhythmic layering and patterns consistent with tidal bedding, support the idea that strong tides operate along the margins of protocontinents and volcanic islands. Wave-driven and tidal processes also influence the exchange of gases between the ocean and atmosphere. At the air-sea interface, molecules of carbon dioxide, methane, nitrogen, oxygen, when present, and other gases continually move between water and air. The direction and rate of this exchange depend on the concentration gradients across the interface, the solubility of each gas, and the physical renewal of the surface layer by turbulence and breaking waves. In the Archean, higher partial pressures of carbon dioxide in the air increase the flux of this gas into the ocean until dissolved inorganic carbon species in the water rise to levels where chemical equilibria and precipitation of carbonate minerals balance further uptake. Methane, if present in significant amounts in the atmosphere, also dissolves into the surface ocean, where it can be consumed by chemical reactions or by microbial metabolisms in later Archean times. Hydrogen and other reduced gases emitted from seafloor sources can be transferred upward to the mixed layer and then to the atmosphere. The surface oceans are not chemically inert. They contain dissolved ions derived from weathering of rocks on land, from reactions at the seafloor, and from ongoing volcanic and hydrothermal inputs. Major components include sodium chloride, calcium, magnesium, sulfate bicarbonate, and various trace metals, though the relative proportions differ from modern seawater. Geological evidence and modeling suggest that Archean seawater is rich in dissolved ferrous iron, because low oxygen levels in the atmosphere and upper ocean allow iron to stay in a reduced soluble form. This ferrous iron can be transported widely in the oceans until it encounters local conditions that favor oxidation and precipitation as iron-rich minerals, some of which appear in banded iron formations deposited on the seafloor. The surface mixed layer exchanges iron-carbon and other species with deeper waters through mixing and overturning, so large-scale circulation helps distribute these chemical constituents around the globe. Carbon in the ocean exists in several forms, including dissolved carbon dioxide bicarbonate and carbonate ions. The relative abundance of these species depends on temperature pressure and the total amount of dissolved inorganic carbon, as well as on the alkalinity provided by dissolved cations such as calcium and magnesium. In the Archean, high atmospheric carbon dioxide and active silicate weathering likely raise the total carbon content of the oceans. When carbonate saturation levels in certain surface waters are exceeded, calcium carbonate minerals can precipitate, especially in warm, shallow environments where evaporation and biological processes concentrate ions. These precipitates accumulate as sediments and remove carbon from the short-term climate system. Although in the early and middle Archean, the magnitude and global distribution of such carbonate deposition remain uncertain. The surface ocean also holds nutrients such as phosphorus and fixed nitrogen in forms that can be used by microbial life. Their concentrations are set by a balance between sources, including river input from land and upwelling of deep water, and sinks, such as burial in sediments. In the Archean, with limited continental area and different oxidative conditions, the cycling of these nutrients likely differs from modern patterns, but they still control where and how rapidly microbial communities can grow in the sunlit surface layers. Light penetration into the ocean controls the thickness of the photic zone, the depth range within which photosynthetic organisms can harvest light energy. Organic haze and atmospheric composition affect the spectral quality and intensity of light that reaches the sea surface, while water itself absorbs and scatters light with wavelength-dependent efficiency. In the Archean, with little or no ozone, more ultraviolet light reaches the top of the ocean, but absorption by water and dissolved substances quickly reduces its intensity with depth. Visible light penetrates more deeply, especially in the blue-green range, giving a photic zone that may extend to tens of meters or more depending on water clarity. In surface waters within this zone, early photosynthetic microbes, including cyanobacteria in later Archean times, use photons to drive chemical reactions that fix carbon, and in some cases release oxygen as a byproduct. Even before oxygenic photosynthesis becomes widespread, other phototrophic metabolisms using different pigments and electron donors may operate in the photic zone, drawing on dissolved iron or sulfide. The physical structure of the surface ocean with its mixing stratification and currents determines where stable layers of illuminated water form and how often they are renewed with nutrients from below, thereby controlling the geographic distribution of these primary production processes. Temperature and salinity combine to set the density of seawater, so patterns of evaporation, precipitation, river input, and ice formation, when present, all influence the structure of the surface ocean. In low-latitude regions with strong evaporation, surface waters become warmer and saltier, tending to increase density and potentially drive sinking if cooling or mixing occurs. In high-latitude or upwelling regions, cooler and sometimes fresher waters occupy the surface, promoting different circulation patterns. In the Archean, the balance among these mechanisms may differ from later times. Because of the overall warmer climate, the configuration of continents, and the presence or absence of ice, but the basic physical relationships still apply. Density-driven flows together with wind and tidal forcing shape the full three-dimensional circulation of the oceans. Over very long periods, the combined action of these physical and chemical processes in the surface ocean helps regulate the climate and the composition of both ocean and atmosphere. Uptake and release of carbon dioxide in the mixed layer buffer changes in atmospheric levels, while precipitation and burial of carbonates and organic matter remove carbon from the short-term cycle. Exchange of gases maintains near equilibrium between dissolved and atmospheric species under given conditions so that shifts in one reservoir affect the other. Mixing and advection distribute heat and solutes, preventing extreme local accumulation and tying the system together on a global scale. In the Archean Eon, the surface oceans with their waves, tides, currents, and chemically active waters act as an intermediate layer in the chain of processes that connect atmospheric forcing from above to geological and biological activity below, providing a dynamic environment in which early life and geochemical cycles begin to interact on a planetary scale. In the Archean Eon, the global oceans act as a vast chemical reservoir that links the atmosphere crust and interior through slow but continuous exchanges of dissolved substances. At the broadest scale, the composition of seawater reflects the balance between inputs from weathering on land and at the seafloor outputs into sediments and altered crust, and internal reactions that transform one dissolved species into another. Direct samples of Archean seawater do not exist, but minerals that form from marine waters. Fluid inclusions in ancient crystals and chemical signatures preserved in sedimentary rocks provide indirect constraints. These lines of evidence suggest that the total salinity of Archean seawater is of the same order as, and perhaps somewhat lower than or comparable to, that of later eras, though exact values remain uncertain. Sodium and chloride ions are likely already the dominant contributors to salinity, because they are supplied in large amounts by the breakdown of crustal rocks, and are relatively conservative once in solution, meaning that they are not easily removed except by physical isolation and evaporation. Other major cations such as calcium and magnesium and anions such as bicarbonate and sulfate are also present, but their relative proportions differ from those in modern oceans. Elevated levels of atmospheric carbon dioxide and active interaction between seawater and basaltic oceanic crust add large quantities of dissolved inorganic carbon and cations to the ocean. When rainwater and river water acidified by dissolved carbon dioxide react with exposed rocks on protocontinents and volcanic islands, they dissolve alkali and alkaline earth elements and carry them to the sea. At mid-ocean ridges and other sites of hydrothermal circulation, seawater percolates into hot crust, reacts with basalt, and returns to the ocean enriched in certain ions and depleted in others. Although the detailed processes at these vents are treated later, their integrated effect on the bulk ocean is to adjust the ratios of magnesium to calcium, to add metals such as iron and manganese, and to influence the alkalinity of seawater. In the Archean, higher internal heat flow and more active crust production mean that hydrothermal exchange is especially vigorous. So the ocean's composition is strongly shaped by seafloor reactions as well as by continental weathering. One result is a likely difference in the magnesium to calcium ratio of Archean seawater compared with modern values, with some indications pointing toward relatively lower magnesium and higher calcium, though there is still debate and uncertainty. This difference affects the kinds of carbonate minerals that tend to precipitate and the ease with which certain sedimentary rocks form. The dissolved inorganic carbon system in the Archean Ocean consists mainly of carbon dioxide bicarbonate and carbonate ions, whose relative abundances are controlled by pH and total carbon content. High atmospheric carbon dioxide and active exchange at the surface push more carbon into the ocean, while reaction with silicate minerals on land and in basaltic crust consumes carbon dioxide and releases cations that increase alkalinity. The combined effect may lead to seawater that is at least mildly alkaline on average, though some studies propose intervals of more neutral or even slightly acidic conditions in specific settings. Because free oxygen in the atmosphere is very low, the redox state of the ocean is also very different from that of later times. Most of the water column is anoxic, meaning that it lacks dissolved oxygen, and reduced species such as ferrous iron and dissolved sulfide can persist in solution where they would be quickly oxidized today. Geological evidence from iron-rich sedimentary deposits indicates that large parts of the Archean Ocean, especially at depth, are ferruginous, with high concentrations of dissolved ferrous iron. This iron originates from weathering of rocks on land under low oxygen conditions and from hydrothermal fluids that leach iron from basalt and deliver it in a reduced form to the sea. As long as the water remains devoid of strong oxidants, this ferrous iron stays in solution and can be transported over great distances by currents. Where conditions favor partial oxidation, for example, in surface waters exposed to even small amounts of oxidizing power from early photosynthetic activity, or from photochemical reactions in the atmosphere, some of this iron converts to ferric forms that are much less soluble. The resulting iron oxides and hydroxides precipitate and settle to the seafloor, forming layers of iron-rich sediment that later become banded iron formations. The alternation of iron-rich and silica-rich bands in some of these rocks suggests that the supply of oxidants, the rate of iron input, or the degree of mixing between different water masses, varies on time scales from seasonal to much longer, leading to cyclic changes in the intensity of iron precipitation. Dissolved silica is another major component of Archean seawater. At high temperatures and under low biological demand, silica solubility is relatively high, and without abundant silica, using organisms such as diatoms or radiolarians, there are few efficient biological sinks to remove it from solution. Hydrothermal systems at spreading centers and in volcanic regions supply silica-rich fluids to the ocean, and weathering of silicate minerals on land releases additional silica. As a result, the concentration of dissolved silica in Archean oceans is likely higher than in more recent times. Oversaturation with respect to certain silica minerals can lead to the precipitation of chert, a microcrystalline form of quartz that forms from the slow accumulation and recrystallization of silica-rich sediments. Many Archean sedimentary sequences contain thick chert units, sometimes interlayered with iron-rich bands pointing to an ocean that carries large amounts of dissolved silica and periodically deposits it under the right physical and chemical conditions. The sulfur cycle in the Archean Ocean also differs from that of later oxygen-rich times. Volcanic emissions and hydrothermal fluids introduce sulfur into the atmosphere and ocean mainly in reduced and oxidized forms, such as hydrogen sulfide and sulfur dioxide. In the absence of abundant oxygen, much of this sulfur ends up in the ocean as dissolved sulfide or as intermediate valent species. The concentration of sulfate, the fully oxidized form of sulfur, appears to be much lower than in modern seawater, as indicated by the scarcity of large sulfate evaporate deposits and by isotopic signatures in Archean sulfide and sulfate minerals. Reduced sulfur can accumulate in anoxic or low sulfate environments, and in some restricted basins or boundary layers where sulfate does exist, microbial or abiotic reduction can produce sulfide that reacts with dissolved iron to form iron sulfide minerals, such as pyrite. The relative scarcity of sulfate limits the extent of widespread sulfidic or euxinic conditions in the open ocean, but local sulfidic zones may still develop near some sediment-water interfaces or in partly isolated basins. Trace metals, including elements such as copper, zinc, nickel, and molybdenum, circulate through the Archean oceans in forms that depend on pH redox state and the presence of ligands that can complex with metal ions. In a largely anoxic, ferruginous ocean, many of these metals behave differently than in modern oxygenated seawater. Some may remain more soluble and widely distributed, while others are scavenged by iron oxides when and where those precipitate. These patterns influence the availability of metals that can serve as cofactors and enzymes for early metabolic pathways, though direct links must be drawn with caution given the limited record. Phosphorus, an essential nutrient for life, is delivered to the ocean by weathering of continental and oceanic crust and is removed mainly by burial with sediments. Its concentration in Archean seawater is not well constrained, but it too is regulated by interaction with iron minerals and by the redox state of the water column. At the broad scale, the chemical structure of the Archean Ocean tends to separate into layers with different redox and compositional characteristics. Surface waters in direct contact with the atmosphere and influenced by photosynthetic organisms in later Archean times may become slightly more oxidizing than deeper layers, especially in well-lit productive regions. Below, vast volumes of water remain anoxic and rich in ferrous, iron, and silica. Interfaces between these layers, sometimes called redox clines, are zones of strong chemical gradients where many reactions occur as reduced and oxidized species meet. The position and sharpness of these boundaries depend on mixing circulation and the strength of sources and sinks of oxidants and reductants. Over geological time, the large-scale chemical cycles of carbon, iron, sulfur, phosphorus, and silica in the Archean Ocean are governed by the slow but persistent exchange of material between water, atmosphere crust, and sediments. Carbon moves between atmospheric carbon dioxide, dissolved inorganic forms, carbonate minerals, and organic matter. Iron cycles between dissolved ferrous states, precipitated oxides and sulfides and minerals in altered crust. Sulfur shifts among reduced volcanic gases, dissolved species and mineral sulfides and sulfates. These cycles are not yet influenced by complex multicellular ecosystems, but they are already shaped by physical processes such as circulation and mixing, by chemical equilibria and kinetics, and by the earliest microbial metabolisms that tap into available gradients. At the scale of the whole planet, the composition of Archean seawater represents the integrated outcome of all these processes, providing the medium in which later, more localized environments such as seafloor basins, hydrothermal systems, and sediment pore waters develop their own distinct chemical signatures. In the Archean Eon, the floor of the global ocean forms the solid boundary that receives material from above and delivers heat and dissolved substances from below, acting as both a physical foundation and a reactive interface. Most of this seafloor consists of mafic oceanic crust rich in iron and magnesium that has formed at spreading centers where upwelling mantle melts and solidifies, then moves away as new crust is created. Because internal heat flow in the Archean is higher than in later times, seafloor spreading is generally more vigorous, and young oceanic crust is hotter and more buoyant. This leads to a landscape of broad mid-ocean ridges, elevated plateaus, and thinner, less dense lithosphere compared with more recent eras. Newly formed crust near spreading centers stands higher above the underlying mantle, so the seafloor there lies at relatively shallow depths beneath the sea surface. As crust moves away from these zones, it cools, contracts, and becomes denser, gradually subsiding and forming deeper ocean basins. The result is a seafloor topography with large-scale variations in depth from ridge flanks and volcanic plateaus to abyssal plains and deeper troughs, even though the detailed shapes and exact depths are not preserved. In some regions, large igneous provinces may build substantial submarine plateaus, while in others, crustal thinning and flexure produce elongated basins and proto-trenches. Over these solid structures, the ocean deposits sediments that record conditions in the water column and at the sea surface. The uppermost layer on much of the Archean seafloor consists of fine particles that slowly settle out of the water. These include clay-sized fragments derived from weathering on land and transported by rivers, wind-blown dust, and tiny mineral grains and colloids that form directly in the water column from chemical reactions. Because continents are smaller and more fragmented, the total flux of terrigenous clastic material to the deep ocean may be lower than in later eras, and much of it accumulates near land margins and in shallow seas. Farther from land sediments are dominated by chemical precipitates such as chert and iron-rich layers, along with any organic matter produced in the overlying waters that survives degradation during sinking. The rate at which these particles accumulate is generally slow, so thick sedimentary sequences require long periods of relatively continuous deposition. In deep basins that remain stable and below the reach of strong currents or turbidity flows, very fine laminations can preserve subtle variations in input from year to year or over longer cycles, though many Archean successions have later been deformed or metamorphosed, obscuring the original structures. Closer to emergent land and along the flanks of protocontinents and volcanic islands, the seafloor receives coarser sediments. Rivers deliver sand, silt, and gravel to coastal zones where waves and tides redistribute them along shorelines and across continental shelves. Storms can resuspend these sediments and move them offshore, while gravity-driven flows called turbidity currents can carry dense mixtures of water and suspended particles down slopes into deeper basins. When these flows slow, they deposit characteristic graded beds with coarse grains at the bottom and finer material above. Such deposits preserved in Archean turbidite sequences indicate that similar processes operate even in this distant time, shaped by gravity-fluid dynamics and the interaction between sediment supply and basin topography. Cross-bedding ripples and other sedimentary structures within Archean sandstones and siltstones record the directions and strengths of currents, tides, and waves in ancient shallow marine environments, providing indirect evidence for seafloor conditions at the time of deposition. In many Archean basins, chemical sediments play a larger role than in later eras. Thick successions of banded iron formations composed of alternating iron-rich and silica-rich layers accumulate on the seafloor, often in relatively deep water settings below the direct influence of strong wave action. These deposits form as dissolved ferrous iron in the ocean is oxidized and precipitated as iron oxides or related minerals, while silica-rich layers reflect oversaturation of dissolved silica and its subsequent precipitation as chert. The exact triggers for each pulse of iron and silica deposition are still debated, but they likely involve changes in the supply of oxidants, variations in hydrothermal input, and shifts in ocean circulation that alter the mixing between iron-rich deep waters and more oxidizing surface layers. Over time, the accumulation of these banded iron formations records both the chemical state of the ocean and the vertical structure of the water column above the seafloor, even though later metamorphism often recrystallizes the original minerals. Other chemical sediments include carbonate rocks that precipitate from seawater when local conditions favor supersaturation with respect to calcium carbonate. In the Archean, such conditions are common in warm, shallow marine settings on and around protocontinental shelves and platforms. There, water warmed by sunlight and enriched in dissolved inorganic carbon and calcium can lose carbon dioxide to the atmosphere or consume it through reactions driving the system toward carbonate precipitation. Carbonate mud and early cement form in place on the seabed, sometimes trapping small fragments and early microbial communities. Over time, these materials lithify into limestones and dolostones that preserve information about seawater chemistry, temperature, and the presence of early life. In deeper settings, carbonate sediments may be rarer if the water column becomes undersaturated with respect to calcium carbonate at depth, causing shells or grains that sink below a certain level to dissolve. The position of this depth, sometimes called the carbonate compensation depth, depends on the total carbon content of the ocean pressure temperature and other factors, and in the Archean, it may lie at different depths than in later times. The shape and evolution of Archean basins are controlled by the behavior of the lithosphere under the influence of internal heat and tectonic forces. Where new crust forms at spreading centers, thermal subsidence as it cools creates space that can be filled with sediments and water-forming oceanic basins. Along the margins of protocontinents, flexure, under the weight of thickened crust and volcanic edifices, can generate peripheral basins that collect sediments eroded from adjacent highlands. In regions where crustal blocks converge, early forms of subduction or other styles of crustal thickening may create deeper basins and troughs on the overriding plates, though the exact tectonic regime remains a subject of active research. These basins serve as repositories for sediments of various types, stacking layers of clastic chemical and, in some cases, volcanic material that together record a history of seafloor conditions and overlying water properties. As sediments accumulate, they begin to compact under their own weight, expelling pore waters and increasing in density. In the Archean, higher heat flow means that buried sediments often experience elevated temperatures at shallower depths than in later times, promoting early diagenetic reactions that transform the mineralogy and texture of the deposits. Clay minerals may convert to more stable forms. Carbonate cements can grow and recrystallize, and organic matter can be altered. These processes change the porosity and permeability of the sedimentary pile and modify its ability to interact chemically with circulating fluids. Pore waters moving through sediment columns carry dissolved species between layers, mediating reactions such as the reduction of iron oxides by organic material or the precipitation of sulfide minerals, where reduced sulfur and iron meet. Although the detailed micro-scale environment of these reactions belongs to a more inward part of the system, their integrated effect on the seafloor is to create vertical and lateral patterns of mineralogy and chemistry that reflect both depositional and post-depositional histories. The seafloor is not a static surface even during periods of relative tectonic quiet. Small-scale faulting crustal flexure and differential loading by sediments cause parts of the oceanic crust to uplift or subside over time. These movements change local water depths, influence the types of sediments that accumulate, and sometimes expose previously buried layers to erosion. Where uplift brings portions of the seafloor into shallower water or even above sea level, wave action and weathering can rework older sediments and volcanic rocks, creating new particles that are transported back into the ocean. Conversely, ongoing subsidence can create accommodation space for thick sedimentary sequences, preserving a long record of changes in ocean chemistry and circulation. Over hundreds of millions of years, this interplay between sedimentation subsidence and uplift continually reshapes the Archean seafloor. Heat flowing from the mantle through the oceanic crust also influences seafloor conditions. Young crust near spreading centers is hot, and its elevated temperature drives vigorous circulation of seawater through fractures and porous zones, although the detailed behavior of these hydrothermal systems is considered separately. More broadly, the higher background geothermal gradient in the Archean means that the temperature at a given depth below the sea floor is higher than in later times. This gradient affects the stability of minerals, the rates of chemical reactions in sediments, and the behavior of fluids. It can promote the release of water and other volatiles from minerals as they are buried and heated, contributing to fluid flow through the crust and into the overlying ocean. Even away from major tectonic boundaries, this internal heat subtly shapes the environment at the base of the ocean by setting the conditions under which rocks and sediments evolve. Sedimentary deposits accumulating on the Archean seafloor serve as a primary archive of environmental conditions in this eon. Their composition, layering, and internal structures capture information about ocean depth energy, of the water column sediment supply, and the chemical state of seawater. For example, sequences that transition from coarse shore-face sandstones to finer offshore shales, and finally to deep water chemical sediments, record the progressive deepening of a basin. Alternating bands of iron-rich and silica-rich layers and banded iron formations track changes in the availability of oxidants and dissolved iron. Carbonate platforms with particular isotopic signatures reveal aspects of the carbon cycle and possible hints of biological activity. Even though later metamorphism and deformation have altered many Archean rocks, careful analysis of their remaining features allows reconstruction of aspects of seafloor topography and sedimentary environments. In this way, the Archean seafloor, though long since transformed, provides evidence for how the ocean floor functions as an intermediate layer between the overlying water column and the deeper crust, regulating the accumulation of sediments, the exchange of chemicals, and the long-term storage of materials that move through the Earth system during this early chapter of planetary history. In the Archean Eon, the seafloor not only receives sediments from above, but also hosts circulation of seawater through hot crust, giving rise to hydrothermal systems that connect the deep interior to the oceans. At spreading centers and other volcanically active regions, fractures and porous zones in newly formed basaltic crust allow cold seawater to percolate downward. As this water moves deeper, it encounters rocks heated by underlying magma bodies and by the higher geothermal gradient of the Archean. The water warms, reacts with surrounding minerals, and becomes less dense, so buoyancy forces drive it back toward the surface along separate pathways. This circulation sets up a loop in which seawater enters the crust, is transformed chemically and thermally, and then returns to the ocean through vent fields on the seafloor. The chemistry of the fluids changes during their passage through hot crust. As seawater heats, it dissolves elements from basalt, including iron, manganese, copper, zinc, and other metals. It exchanges ions with the rock, losing much of its magnesium to newly formed minerals and gaining calcium and other cations. Sulfate in the original seawater, present at lower concentrations than in later eras, can be reduced to sulfide in the hot reducing conditions of deep circulation zones. Water rock reactions produce hydrogen gas, and in some settings, methane and other reduced compounds. As a result, the fluid that emerges at the seafloor is often rich in metals, hydrogen and sulfide, depleted in magnesium and sulfate, and distinct in pH and temperature from the surrounding bottom water. Some vent fluids in such a setting are very hot, reaching temperatures close to the local boiling point under seafloor pressure conditions, while others are cooler, forming diffuse flow zones where altered water seeps through sediments and porous rocks. Where focused upflow channels reach the seafloor, hot hydrothermal fluids exit into much colder and more oxidizing seawater. At these discharge points, gradients in temperature, pH, redox state, and chemical composition arise over distances of centimeters to meters. Buoyant plumes of vent fluid rise and entrain ambient water, cooling and diluting as they move upward. Metals and sulfide in the fluid combine to precipitate minerals that build chimneys and mounds around vent openings. Silica can also precipitate as the fluid cools, coating structures or forming separate deposits. These constructions can grow over time as long as hydrothermal flow continues, providing a physical record of vent activity. In the Archean, elevated heat flow and widespread magmatic activity likely make such hydrothermal fields common along spreading ridges and volcanic plateaus. The mixing zones around vents are places where chemical gradients are strong. Reduced species such as hydrogen, ferrous iron, and sulfide from vent fluids meet oxidized species in seawater, including any dissolved oxygen in later Archean intervals and oxidized forms of carbon and sulfur. Even in early Archean times, with almost no free oxygen, oxidants produced by photochemical reactions in the atmosphere or by local redox cycling can be available. At the same time, steep temperature gradients exist from near vent temperatures at chimney interiors to ambient bottom water a short distance away. pH can shift from acidic values in the fluid to more neutral values in the background ocean. These combined gradients provide a range of microenvironments across vent structures, in surrounding sediments, and within the porous crust where fluids spread laterally before exiting. Beyond the immediate vent sites, hydrothermal plumes carry modified water into the wider, deep ocean. As hot plumes rise, they entrain and mix with ambient water until they reach a level where their density matches that of the surroundings, then spread laterally as layers that can travel long distances under the influence of deep currents. These plumes distribute heat metals and other dissolved species over broad areas. In the Archean, this process contributes to the presence of dissolved ferrous iron and manganese in deep waters because vent fluids inject these elements into an ocean that lacks strong oxidizing capacity. Over time, some of the injected components precipitate and settle to the seafloor, contributing to chemical sediments such as iron formations and manganese-rich layers, while others remain in solution and join the general inventory of oceanic solutés. Hydrothermal circulation also alters the crust itself. As seawater-derived fluids move through basalt and deeper rocks, they change the mineralogy and physical properties of the host. Original minerals react to form secondary assemblages, locking some elements into solid phases and releasing others back into the fluid. Porosity and permeability can increase or decrease depending on the balance between mineral dissolution and precipitation. In some zones, fracture networks are widened, enhancing fluid flow, while in others, mineral growth can clog pathways and redirect circulation. Over long periods, this alteration transforms the upper portion of oceanic crust into a geochemical filter that modulates the exchange of elements between mantle-derived rocks and the ocean. In the Archean, with faster crust production and higher heat flow, a larger fraction of the seafloor may be in a state of active hydrothermal alteration at any given time than in later eras. Hydrothermal systems are not limited to mid-ocean ridges. Volcanic arcs, back arc basins, and hotspot-related plateaus where magma rises close to the seafloor also host circulating fluids. In these environments, the composition of vent fluids can differ from those at spreading centers because of variations in rock-type pressure and the presence of magmatic volatiles. Some systems discharge relatively low-temperature fluids enriched in specific metals or gas mixtures, while others resemble high-temperature ridge vents. The heat carried by hydrothermal circulation forms a component of the way the Archean Earth loses internal energy, complementing conductive heat loss and magmatic eruptions. By transferring heat from deep within the crust to the ocean, these systems influence local temperature at the seafloor and contribute to the thermal state of the deep ocean. At the same time, the chemical transformations that occur along flow paths and at vent outlets help set the composition of seawater on long time scales. Elements move between rock and sea in these reactions, and the balance of these exchanges contributes to the stability of ocean salinity and major ion ratios. In the Archean Eon, hydrothermal systems at the seafloor act as mediators between the hot interior and the overlying ocean, creating localized chemical and physical gradients that feed into broader geochemical cycles and establish environments distinct from those in the open water column or on deep-sea sediments nearby. In the Archean Eon, the solid crust of the Earth is thin, hot, and highly active compared with that of later times, and it plays a central role in controlling how gases move between the interior, the oceans, and the atmosphere. Most of the crust beneath the oceans forms when mantle material partially melts, rises and erupts or intrudes at spreading centers and other upwelling zones. As melts reach the surface or solidify at shallow depths, they build new basaltic crust that is rich in iron, magnesium, and volatile-bearing minerals. Above subaerial volcanic centers on protocontinents and volcanic islands, magmas ascend through thicker parts of the lithosphere, feeding eruptions that build cones, plateaus, and lava fields. In both submarine and subaerial settings, volcanic activity releases gases that were dissolved in the melt or stored in minerals, transferring volatiles from the interior to the surface environment. The main gases released include water vapor, carbon dioxide, hydrogen, sulfur, bearing species such as sulfur dioxide and hydrogen sulfide, and smaller amounts of methane and carbon monoxide. In the Archean, when the mantle is hotter and melts are generated more readily, the overall rate of volcanic outgassing is higher than in later eras, though the exact magnitude is uncertain. Many of these gases enter the atmosphere directly from vents, fumaroles, and explosive eruptions, while others pass first into shallow hydrothermal systems and then into the ocean. Water vapor is the most abundant volcanic gas, and over long periods, repeated eruptions contribute a significant fraction of the water that resides in the oceans and atmosphere. Carbon dioxide is another major product, and its steady supply from arcs hotspots and ridge-related volcanism helps maintain the elevated levels needed to keep the Archean surface warm under a faint sun. Hydrogen and reduced carbon and sulfur species inject chemical potential into the near-surface environment, providing substrates for redox reactions in the atmosphere, in surface waters, and in subsurface niches. The balance between different volcanic settings influences the composition of outgassed mixtures. Volcanism above early subduction or subduction-like zones tends to produce fluids enriched in water and carbon dioxide, derived from hydrated and carbon-bearing rocks that are heated and partially melted as they descend. Hotspot and plume-related volcanism can bring up mantle-derived melts that carry a different signature of volatiles, including more carbon monoxide and hydrogen. In submarine eruptions, much of the volatile content of lava may be quenched into glass and released gradually through hydrothermal circulation, while explosive subaerial eruptions can inject pulses of gases and fine ash high into the atmosphere over short intervals. As volcanic gases mix with the Archean air and dissolve into surface waters, they take part in reactions that help establish the atmospheric and oceanic composition. Carbon dioxide dissolves in rain and seawater to form carbonic acid, which reacts with silicate minerals in newly formed crust and on exposed land surfaces, breaking them down and releasing cations that rivers carry to the ocean. There they combine with bicarbonate to form carbonate minerals that eventually precipitate and become part of the sedimentary record. In this way, volcanic outgassing of carbon dioxide is coupled to silicate weathering and carbonate formation, forming a feedback that can over long times moderate atmospheric carbon dioxide levels. In the Archean, this cycle operates in the context of smaller continental areas and more rapid crust production, but the same reactions link gas release, rock alteration, and carbon burial. Sulfur dioxide and hydrogen sulfide released from volcanoes undergo oxidation reduction and disproportionation reactions in the atmosphere and ocean-forming sulfate elemental sulfur and sulfide. Under low oxygen conditions, sulfate remains a minor component of seawater, while sulfide can accumulate in some environments and react with dissolved iron to form pyrite and other sulfide minerals. The isotopic composition of sulfur in Archean rocks records these pathways and also shows evidence of mass-independent fractionation, a signal that arises from photochemical reactions in an atmosphere with very low oxygen and ozone. Volcanic sulfur outgassing therefore not only contributes to aerosol formation and cloud condensation nuclei, but also leaves a durable imprint that helps constrain the redox state of the early atmosphere. The crust that supplies and receives these gases is constantly replaced and reworked. At spreading centers, newly formed oceanic lithosphere moves away from the ridge axis as more melt is added. As it travels, it cools, thickens, and interacts with seawater through hydrothermal alteration, taking up water and other elements into its mineral structure. Eventually, this dense, cooled lithosphere returns to the mantle in some form of subduction or foundering, although the exact style remains debated. In all reasonable scenarios, materials that have interacted with the surface environment are eventually returned to depth, where they release some of their volatiles again during heating and partial melting. This return flux closes the long-term cycle of volatiles between mantle and surface. Archean continental crust forms mainly through processes that differentiate basaltic magmas into more silica-rich compositions. At convergent margins or other zones of crustal thickening, melting of hydrated basaltic crust produces tonalite, trondhjemite, and granodiorite rock types that are common in Archean cratons. These rocks are less dense than the surrounding mafic crust, so they can accumulate as relatively buoyant blocks that resist recycling and become the nuclei of early continents. As these protocontinents grow and stabilize, they provide larger areas of land for weathering and erosion, increasing the efficiency of chemical reactions that draw down carbon dioxide and supply ions to the ocean. The growth of continental crust thus feeds back into the atmospheric and oceanic composition by changing the area and nature of the surface exposed to air and water. At the same time, volcanism continues along their margins and in interior rift zones, returning volatiles to the atmosphere. Over hundreds of millions of years, the combination of crust formation, volcanic outgassing, hydrothermal alteration, weathering sedimentation, and crustal recycling establishes linked cycles that move water, carbon, sulfur, and other volatile elements between the mantle, crust, oceans, and atmosphere. In the Archean Eon, these cycles operate under boundary conditions set by higher internal heat flow, smaller and more mobile continents, and a largely anoxic atmosphere and ocean. The crust remains the interface where deep earth processes express themselves at the surface through volcanism and uplift, and where surface processes modify rock and trap volatiles in sediments that may later be returned to depth. In this way, crustal processes and volcanic outgassing function as a central part of the Archean Earth system, linking internal heat and composition to the evolving oceans and air. In the Archean Eon, the continents that later anchor stable cratons are only beginning to grow, and much of the planet's solid surface still lies beneath the oceans. The crust that stands above sea level or in very shallow water is thicker, more silica-rich, and more buoyant than the surrounding basaltic seafloor, having formed through repeated episodes of melting intrusion and volcanic accumulation. Early in this process, small blocks of relatively light crust composed mainly of tonalite, trondhjemite, and granodiorite rise above denser mafic rocks and assemble into protocontinental fragments. These blocks form where hot basaltic crust and underlying mantle materials are partially melted, often in regions of convergent flow or crustal thickening, producing magmas enriched in silica and alkali elements. As these magmas crystallize and are reworked, they give rise to thickened crustal roots that resist recycling. Over time, collisions, lateral accretion, and magmatic underplating cause these fragments to merge into larger domains, some of which will evolve into the long-lived cores of later continents. At the surface, these buoyant crustal blocks interact with the surrounding ocean, creating a pattern of shallow seas, island arcs, and narrow continental shelves. The relative sea level around each protocontinent depends on the balance between crustal thickness thermal state and global ocean volume. In the hotter Archean Earth, freshly formed continental lithosphere may be more thermally expanded and therefore sit somewhat higher, yet tectonic subsidence flexure under volcanic loads and local extension can easily create low-lying areas that flood with seawater. The result is a shifting mosaic of emergent land coastal plains and broad, warm, shallow marine platforms. These shallow seas are zones where atmosphere, ocean, and crust meet under conditions favorable to chemical reactions and sediment accumulation. Wave action and tides, which are strong in the Archean due to the closer moon, continually stir the water and rework the seafloor in these environments. On open coasts, wave energy abrades exposed rock, generating sand and gravel that form beaches and shore-face deposits. In more sheltered embayments and behind islands, finer sediments such as silt and clay settle out to form mudflats and lagoonal deposits. Tidal currents move these materials back and forth, sculpting ripples and crossbeds that will later be preserved in lithified sandstones and siltstones. Because continental vegetation is absent, slopes and surfaces of exposed rock respond directly to rainfall and runoff. Chemical weathering by carbon dioxide-rich rainwater dissolves minerals and releases ions such as calcium, sodium, potassium, and silica into streams, while physical weathering fragments rock into clasts of various sizes. These products are carried to the coastal zone, where they enter the shallow seas and become part of the sediment load. The interaction between weathering on land and deposition in shallow marine settings couples the growth of continental crust to the chemistry of the ocean, since the ions released on land help set seawater composition, and the sediments along margins record both source rock types and environmental conditions at the time of burial. Many Archean shallow marine environments are sites of carbonate precipitation. In warm, sunlit waters above carbonate-saturated seawater, the combination of evaporation gas exchange with the atmosphere and local microenvironments promotes the formation of calcium carbonate minerals. These precipitates can accumulate as fine carbonate muds on broad platforms, build up as grainy shoals, or cement existing sediments into coherent layers. Over time, repeated cycles of flooding, sedimentation, and early lithification create stacks of carbonate rocks that fringe or cap the protocontinental blocks. Their isotopic compositions reflect the balance between volcanic carbon dioxide input, silicate weathering, and any organic carbon burial, providing clues to the state of the carbon cycle during the Archean. In addition to carbonates, shallow seas around growing continents host deposits of siliciclastic sediments derived from erosion of crustal rocks. River systems that drain the interior of protocontinents deliver sand and silt to deltas and estuaries, where they build lobes and channels that shift over time. Storm surges and tidal currents redistribute these materials along strike-forming shore face and shelf deposits that may grade seaward into deeper water muds and chemical sediments. The vertical stacking of such units captures changes in relative sea level sediment supply and tectonic subsidence, showing that Archean continental margins experience repeated cycles of uplift erosion and inundation. The architecture of protocontinents evolves as magmatic intrusions, volcanic additions, and deformation reshape their interiors. Granitic plutons intrude older rocks, thickening the crust and adding heat that can drive further melting and metamorphism. Faulting and folding accommodate horizontal movements, and adjust crustal thickness. In some regions, rifting opens new basins within continental blocks, creating interior seas where shallow water conditions can persist for long periods. In others, compressive forces stack crustal slices and raise mountain belts that supply detritus to adjacent basins. Even though these mountains are rapidly eroded in the absence of stabilizing vegetation, their brief existence enhances the delivery of sediments and solutes to shallow seas. Over longer timescales, the area of exposed continental crust helps regulate atmospheric carbon dioxide through the silicate weathering feedback. As protocontinents grow and more surface area becomes available for weathering, the potential for carbon dioxide drawdown increases. Although this is balanced by volcanic outgassing and by the higher temperatures that speed weathering reactions. Shallow seas along continental margins are also sites for the burial of sediments that contain both carbonate and, in some settings, organic carbon. When these sediments are buried and isolated from rapid recycling, they remove carbon from the short-term atmosphere-ocean system and store it in the crust. In the Archean, with smaller continents and different redox conditions, the magnitude and distribution of organic carbon burial in such settings is still uncertain, but the basic mechanism of coupling between margin sedimentation and long-term carbon storage is already in place. Over hundreds of millions of years, the repeated growth, erosion, and reassembly of protocontinents lead to the formation of larger continental blocks in the late Archean. These blocks host more extensive shallow seas and more complex sedimentary systems, further enhancing their role in surface processes. The stabilization of some crustal cores into cratons, underpinned by thick, relatively cool lithospheric roots, marks a gradual shift toward a more rigid and enduring continental framework, even as their margins remain tectonically and sedimentologically active and continue to exchange material and energy with the oceans and atmosphere. In the Archean Eon, the solid earth beneath the crust is hotter and more dynamic than in later times, and this internal state controls how the planet moves heat from its deep interior toward the surface. The mantle, a thick shell of solid but slowly deforming rock that extends from the base of the crust down to the core, contains heat from two main sources. One is primordial heat, left over from the energy released during planetary accretion and the giant impact that formed the moon. The other is heat from the decay of radioactive isotopes such as uranium, thorium, and potassium. In the Archean, these isotopes are more abundant than in later eras, so radiogenic heating is stronger. Combined with the residual primordial heat, this leads to a mantle that is several hundred degrees Celsius hotter on average than it is in more recent times. Although exact temperatures at specific depths are not directly measurable and must be inferred from indirect evidence such as the chemistry of ancient lavas. A key clue comes from Archean komatiites, ultramafic volcanic rocks with very high magnesium content that require unusually hot mantle melts. Their presence indicates that parts of the mantle reach temperatures sufficient to produce magmas that erupt as very fluid high-temperature lavas. Such high degrees of partial melting are consistent with a mantle that convects vigorously. Mantle convection is the slow, large-scale movement of solid rock driven by buoyancy differences that arise when hotter, less dense material rises and cooler, denser material sinks. In the Archean, higher internal temperatures reduce mantle viscosity and increase buoyancy contrasts, raising the vigor of convection. This can be described in terms of a higher convective efficiency with thinner thermal boundary layers at the base of the lithosphere and faster flow velocities in the deep interior. Hot upwellings bring material from depth toward the base of the crust, where decompression melting produces basaltic magmas that feed seafloor spreading and volcanic plateaus. Cooler downwellings transport lithospheric material and cooled mantle back downward, allowing heat to be extracted from the interior over long time scales. The style of tectonics that this convection supports in the Archean is the subject of ongoing research and debate. One end-member view proposes that something broadly similar to modern plate tectonics already operates with discrete rigid plates moving across the surface, separating at spreading centers, converging at subduction zones, and sliding past each other along transform faults. The other end-member suggests that the lithosphere behaves more as a single lid that may be stagnant for periods and then undergo episodic overturns, drips, or delamination events when it becomes sufficiently dense or weak. Available geological evidence points toward a system that may occupy an intermediate position or evolve over the course of the eon. Archean greenstone belts and associated granitoid terrains record patterns of deformation, magmatism, and metamorphism that share some features with modern convergent margins such as volcanic arcs and accretionary complexes, including imbricated thrusts, synformal basins, and volcanic rocks with chemical signatures that resemble arc-related basalts. At the same time, the scarcity of very high-pressure metamorphic rocks characteristic of some modern subduction zones and certain differences in metamorphic gradients suggest that subduction, if present, may be shallower, shorter-lived, or thermally different from later examples. In all plausible scenarios, the lithosphere in the Archean is thinner and hotter than in later times. Higher temperatures at given depths make rocks more ductile, meaning they can deform plastically over geological timescales rather than fracturing easily. This property weakens the mechanical strength of plates and may allow gravitational instabilities to develop more readily. Dense portions of thickened crust or cooled lithosphere can detach and sink into the underlying mantle, a process sometimes called delamination or drip tectonics. These sinking blobs carry surface-derived material, including hydrated minerals and sediments, into deeper levels, where they release water and other volatiles as they heat and transform, promoting further melting in adjacent mantle regions. Water plays a significant role in Archean tectonic style. Even in an anhydrous mantle, high temperatures support melting, but the presence of water lowers the solidus of mantle rocks, allowing melting at lower temperatures and depths than would otherwise be possible. Seawater enters the lithosphere through fractures, faults, and pores at mid-ocean ridges and other plate boundaries where it hydrates basalts and deeper rocks, forming minerals that incorporate water into their crystal structures. When these hydrated rocks are later buried and heated, either in subduction-like settings or during foundering of dense lithosphere, they release water into the surrounding mantle. This added water facilitates partial melting and can create zones of flux melting that generate magmas with compositions similar to those seen in Archean continental building rocks. In this way, mantle convection, hydration of the lithosphere, and volcanic and plutonic activity together drive the growth of more buoyant silica-rich continental crust. The pattern of heat loss from the Archean Earth reflects both the convective transport within the mantle and the conductive transfer through the lithosphere. Where upwelling mantle reaches shallow depths, the crust is thin, hot, and often volcanically active, leading to high local heat flow at the surface. This is the case at spreading centers and intraplate hotspots, where seafloor hydrothermal systems remove heat efficiently by circulating seawater through young crust. In contrast, regions underlain by thicker, older and cooler lithosphere, such as early cratonic nuclei, exhibit lower heat flow. Yet even there, the values are higher than in later eras, because the mantle and lower crust are still relatively warm. As time passes, cooling from above and loss of heat through radiation into space gradually reduce mantle temperatures and slow convection. But during the Archean, this long-term trend is still in its early phases. The coupling between mantle convection and surface tectonics in the Archean has several consequences for the distribution of volcanism, crustal thickness, and basin formation. Persistent upwellings beneath certain regions can form large oceanic plateaus, which later may become incorporated into protocontinental masses through collision and accretion. Downwelling zones, whether organized as subduction-like features or as broad foundering regions, can create depressions at the surface where sediments accumulate, forming basins whose fill records changes in ocean chemistry and climate. The lateral motion of lithospheric fragments driven by underlying flow brings different crustal blocks into contact, leading to orogenic events that thicken the crust and further promote continental growth. At the deepest accessible levels, mantle convection also influences the rate at which the core cools. Heat flows from the core into the mantle across the core-mantle boundary, and the efficiency of this transfer depends on the temperature contrast and the convective vigor in the lowermost mantle. In the Archean higher mantle, temperatures might at first seem to reduce this contrast, but vigorous convection can maintain efficient heat extraction from the core by transporting heat away from the boundary. This cooling of the core helps sustain the geodynamo that generates the planetary magnetic field, which in turn affects the magnetosphere and the shielding of the atmosphere from solar wind stripping. Thus, interior convection and tectonic style contribute indirectly to the stability of the surface environment and the persistence of conditions that allow oceans and an atmosphere to remain in place. Over the span of the Archean Eon, mantle convection gradually reorganizes as internal heat declines and continents grow. Early on, smaller, more numerous upwellings and downwellings may dominate, while later, as larger continental blocks assemble and thicken, these continents act as thermal blankets that insulate underlying mantle and focus upwellings at their margins or in adjacent oceanic regions. This evolving pattern influences where new crust is created, where older crust is recycled, and how the surface of the planet is partitioned into oceanic and continental domains. Although many details of Archean tectonic style remain uncertain, the broad picture that emerges is one of a mantle that moves heat and material more vigorously than today, driving rapid cycles of crust formation, modification, and recycling. In this setting, internal heat flow and convection provide the deep engine that underlies the more visible processes of volcanism, seafloor spreading, and continental growth already seen at the surface, linking the outer layers of the Earth to the planet's hot interior during this early stage of its evolution. In the Archean Eon, the shallow margins of oceans and some quieter parts of the seafloor host thin but persistent communities of microorganisms that spread across sediments, rock surfaces, and fragments of early crust. These communities assemble into microbial mats, which are layered structures formed when countless cells grow, divide, and trap fine particles over long periods of time. In warm, sunlit coastal waters on and around protocontinents, tidal flats flood and drain under strong tides driven by the closer moon. Each cycle brings fresh water, dissolved substances, and suspended sediment across low-lying surfaces. On these surfaces, microbial mats establish themselves as cohesive films only fractions of a millimeter to a few millimeters thick. The uppermost layers of the mat interact directly with the overlying water and light, while deeper layers sit in more stable chemical conditions. Over time, the combination of microbial growth trapping of particles and mineral precipitation gives these mats a small but measurable thickness and strength. In carbonate-rich shallow seas where seawater is close to or exceeds saturation with respect to calcium carbonate, microbial mats can guide the accumulation of carbonate sediments. As microbial cells at the mat surface carry out their metabolic activities, they modify the chemistry of the adjacent water film, often raising pH in very small-scale microenvironments during periods of active photosynthesis or other processes. This change can promote the precipitation of carbonate minerals within and just beneath the mat. Fine grains and crystal aggregates form and bind with trapped sediment, gradually turning soft gels into firmer laminae. Repeated over many cycles of burial and renewal, this process builds layered structures that rise above the surrounding seafloor by millimeters to centimeters, and later by tens of centimeters, as they grow upwards toward light. These structures, known in the rock record as stromatolites in the Archean, are living buildups whose outer surfaces are actively colonized by microbial communities. As sediment accumulates on the mat, surface cells move upward or new cells grow on top, maintaining access to light and to dissolved compounds in the water. The result is a fine internal fabric composed of alternating layers rich in organic material and layers rich in mineral precipitates and trapped grains. In some settings, individual stromatolite columns or domes sit close together, forming laterally linked mounds that cover broad areas of the shallow seafloor. In others, more isolated buildups stand amid sheets of less structured microbial carpet. The spacing, shape, and vertical relief of these features reflect a balance between growth rates, sediment supply, water depth, and the frequency and intensity of tidal and storm-related disturbance. Where water depth is shallow and wave energy, moderate stromatolites can maintain their structure with each flooding event, adding a thin layer of sediment that the microbial community quickly stabilizes. Where energy is too high, mats may be ripped up and reworked, limiting buildup and favoring flatter microbial surfaces instead. Microbial mats and films are not restricted to carbonate platforms. In siliciclastic environments, where sediments are dominated by sand and mud derived from erosion of crustal rocks, similar communities develop on tidal flats in estuaries and on subtidal surfaces that receive enough light and nutrients. Here, mats bind loose grains together, reducing erosion by waves and currents, and promoting the formation of cohesive bed surfaces. In some cases, the presence of mats leaves distinctive sedimentary textures, such as wrinkle structures, small domes, and polygonal cracks, that reflect the behavior of cohesive organic rich layers during drying and deformation. These features, when preserved in lithified rocks, provide indirect evidence of microbial mat activity in Archean shallow marine settings. Within the mats, physical and chemical conditions vary strongly over very small distances. At the upper surface, light intensity is highest, and exchange with the overlying water keeps concentrations of some dissolved species close to those in the open environment. A short distance below, only a fraction of the incident light penetrates, and diffusion limits the supply of oxidants or other reactants from above. At greater depths, within only a few millimeters, the mat interior can become anoxic, even when the overlying water holds some oxidizing power. Metabolic reactions in each layer consume and produce different compounds, establishing sharp vertical gradients in oxygen, hydrogen sulfide, ferrous, iron methane, and other species. These gradients are maintained by a combination of diffusion advection through pore spaces and continuous microbial activity. The result is a chemically stratified microenvironment where different organisms can occupy niches defined by both energy sources and electron acceptors. Microbial films also colonize other Archean settings beyond open coastal platforms. Around hydrothermal vent fields and in areas where diffuse warm fluids seep through the seafloor, microorganisms attach to mineral surfaces and form thin layers that exploit local chemical gradients. On chimney walls and within porous deposits, films and small clusters grow where reduced vent fluids meet more oxidized seawater, using the energy released by redox reactions that occur at that interface. In deeper low light or dark environments, mats can spread over soft sediments, where slow but persistent fluxes of chemicals from below and from the overlying water sustain metabolic activity. Although these deeper mats may not build large stromatolitic structures because of limited mineral precipitation or different sediment dynamics, they still create micro-scale gradients and alter the chemistry of pore waters and adjacent bottom water. On emergent land and in supratidal zones where water only periodically covers the surface, microbial communities adapt to cycles of wetting and drying. Thin films colonize the upper parts of tidal flats, the edges of small pools and cracks in rocks. When flooded, they carry out aquatic-style metabolisms, exchanging dissolved gases and nutrients with the thin film of water. When exposed, some retain enough moisture within their matrix and between grains to continue limited activity or to endure until the next inundation. These marginal settings provide transitional habitats between fully marine and subaerial environments and illustrate the flexibility of microbial mats in occupying a range of Archean niches. The presence and persistence of microbial mats and stromatolites influence the physical behavior of sediments and the cycling of elements at local scales. By binding grains together, mats reduce risk suspension and transport stabilizing parts of the seabed and shoreline. They trap fine particles that would otherwise remain in suspension, clarifying the water locally and altering light penetration. They create small topographic variations that redirect flows, leading to preferred pathways for currents and the development of microchannels between mounds. At the same time, their metabolic activity modifies the chemistry of surrounding water and pore fluids, affecting the saturation state of minerals such as carbonates and iron oxides, and promoting precipitation or dissolution depending on conditions. Over long intervals, repeated growth and burial of mats contribute organic material and associated mineral phases to sediments forming thin laminae that add up to significant thicknesses in some Archean formations. The microfabrics of these laminae, including fine layering trapped grains and characteristic textures, provide a durable record of microbial presence even when original organic matter is degraded or transformed. In this way, microbial mats, stromatolites, and films act as small-scale interfaces where physical, chemical, and biological processes intersect. In the Archean Eon, they occupy sunlit shallow waters, parts of the seafloor influenced by hydrothermal activity, and periodically wet surfaces near the edges of land, establishing structured, layered communities that modify their surroundings and create the micro-environmental gradients that the earliest metabolic pathways use to capture and store energy. In the Archean Eon, small-scale environments created by chemical gradients in water sediments and rocks support early metabolic pathways that draw energy from redox differences. Metabolism here consists of reaction sets that move electrons from one compound, the electron donor, to another, the electron acceptor releasing energy that cells capture in chemical form. In the largely anoxic Archean world, many of the main donors and acceptors are inorganic substances present in seawater, hydrothermal fluids, and mineral surfaces. Hydrogen, ferrous iron, reduced sulfur species, methane, carbon monoxide, and simple organic molecules serve as common electron donors, while carbon dioxide protons and, in some niches, limited oxidants such as ferric iron or small amounts of oxygen function as electron acceptors. The specific combinations that occur depend on local temperature, pH, redox state, and the availability of dissolved and mineral-bound species. Because geological evidence for early metabolisms is indirect and often altered by later processes, these pathways are reconstructed by combining isotopic signatures in Archean rocks with constraints from experiments and from the behavior of modern microorganisms that use similar reactions. In many Archean settings, particularly around hydrothermal systems, hydrogen is a key energy source. Water-rock reactions at high temperature produce molecular hydrogen as water interacts with ferrous iron-bearing minerals, creating a flux of reduced gas that enters pore waters and vent fluids. Microorganisms that carry out hydrogen-based metabolisms can use hydrogen as an electron donor to reduce carbon dioxide to methane or to other simple organic compounds. In methanogenic pathways, carbon dioxide serves as the electron acceptor and is converted into methane and water, while releasing energy that cells store in chemical bonds. In other hydrogen-using pathways, microorganisms reduce ferric iron or small pools of sulfate or elemental sulfur, where these species are available, linking hydrogen fluxes to iron and sulfur cycling at small scales. Iron itself supports additional metabolisms. In an ocean where dissolved ferrous iron is widespread, microorganisms can use ferrous iron as an electron donor and oxidize it to ferric iron, coupling this reaction to the reduction of carbon dioxide or other acceptors. When this process is driven by light, it is a form of anoxygenic photosynthesis, using iron. These photoferrotrophs generate ferric iron, which precipitates as iron oxides and hydroxides, and can contribute to the deposition of iron-rich layers in banded iron formations. In deeper or more reducing waters, chemolithotrophic iron oxidizers may act at redox interfaces, where small amounts of oxidants meet ferrous iron-rich water, while in sediments and anoxic zones, other microorganisms reduce ferric iron back to ferrous iron, using organic matter or hydrogen-closing local iron redox cycles. Sulfur cycling also supplies energy. Volcanic and hydrothermal inputs deliver reduced sulfur species, such as hydrogen sulfide, to the ocean, and photochemical and limited oxidative processes generate more oxidized forms, including elemental sulfur and sulfate. Microorganisms that oxidize sulfide or elemental sulfur can gain energy by transferring electrons from these reduced species to acceptors such as ferric iron, or in later Archean intervals, small amounts of oxygen in surface waters. Where light is available, anoxygenic photosynthetic organisms use sulfide as an electron donor, while fixing carbon dioxide into organic matter. In parallel, sulfur-reducing microorganisms in sediments use sulfate, where available as an electron acceptor, and reduce it back to sulfide using organic matter or hydrogen, although low sulfate concentrations limit the overall scale of this pathway. Carbon fixation pathways in the Archean provide the means to build organic molecules from inorganic carbon. Some microorganisms reduce carbon dioxide using energy from redox reactions alone, without light, in processes that are well suited to hydrogen-rich anoxic environments such as hydrothermal systems. Others rely on light-driven processes in the photic zone. Among these, anoxygenic phototrophs use pigments to capture light and drive electron transport chains that ultimately reduce carbon dioxide, but they use donors such as ferrous iron sulfide or simple organics rather than water. Later in the Archean, oxygenic photosynthesis, in which water serves as the electron donor and oxygen gas is produced as a byproduct, becomes increasingly significant. In this metabolism, organisms such as cyanobacteria use pigments to harvest light and fix carbon dioxide, while the oxygen released initially reacts with reduced species in the surrounding environment and does not build up in the atmosphere to high levels, but begins to alter local redox balances in surface waters and sediments. Heterotrophic metabolisms, which rely on preformed organic compounds as electron donors, also operate. Organic matter produced by autotrophs accumulates in microbial mats, in suspended particles, in the water column, and in sediments. Microorganisms that oxidize this organic matter using available electron acceptors such as ferric iron sulfate, where present elemental sulfur or carbon dioxide gain energy and close local carbon cycles. In strictly anoxic settings, fermentation pathways allow partial oxidation of organic substrates to smaller molecules that then feed into other metabolic networks. In this way, the pool of organic carbon in Archean environments is repeatedly recycled, with only a fraction escaping remineralization and being buried in sediments as reduced carbon. At the microscale, these metabolisms are organized around redox gradients that emerge where fluids of different composition meet, or where metabolic activity itself generates chemical stratification. In a microbial mat, phototrophs at the surface absorb light and fix carbon-altering local pH and redox state. Just below, in dimmer light or darkness, organisms exploit the changed conditions, reducing sulfate, ferric iron, or carbon dioxide with hydrogen or organic matter, while deeper still, fermenters break down complex organic molecules into smaller compounds. Diffusion and advection move substrates and products between layers, but reaction rates are fast enough that sharp boundaries persist over distances of millimeters. Similar structures occur around hydrothermal vents, in redox-cline zones of the water column, and in sediment-poor waters beneath the seafloor. Each location hosts a community adapted to its particular set of donors, acceptors, and physical conditions, yet the underlying principle remains the same. Electrons flow down potential gradients, and cells intercept part of that flow to store energy and build biomass. Over the long span of the Archean Eon, the cumulative activity of these metabolisms modifies the redox state of the surface environment by slowly transforming reduced compounds into more oxidized forms and by burying reduced carbon and sulfur in sediments, while volcanic outgassing, hydrothermal fluxes, and weathering resupply reduced species from the interior and keep the redox landscape active within the larger physical and chemical system of the Archean Earth.